Okay, so we're going to talk about the rational method here, and for roadway designers, this is probably what you'll use the most. And I will say I'm going to be part of this and give you the more of a national view of how we teach rational method. MoDOT does a little bit different process to figure out, or method to figure out the rational method. And it's because they have done some research at MoDOT, or had the research done, and the method you guys use works for your conditions. And there are different states around the country that do that. They modify what we teach because we're teaching to a national audience. And MoDOT has refined that to work for your processes and what happens in your state. Okay? So here are our learning objectives. We're going to identify flow paths for estimating the time of concentration. We're going to segment a flow path into appropriate components. We'll estimate peak flows from a single drainage area using the rational method. I'm not sure if we're actually doing that. I guess we are. We're going to do it over a number of areas. And then we're going to adjust the time of concentration. We're going to adjust the time of concentration and peak flow computation. So if you were doing a storm drain design, this is how you would kind of start if you're using the rational method. We're not actually going to get into down in the storm drains, the true design of a storm drain, like sizing it and making sure water doesn't pop out the top. Actually, there's a video out there. I can't remember, some Midwest state.
Minnesota.
It was on an interstate, wasn't it? Or a pretty highly trafficked road. They had a big storm, and you see, it's at night, and you see the cars coming, and suddenly this geyser of water is pouring out of a manhole. The manhole goes flying about 50 feet, and then it subsides, and you see the cars going by again, and then it just happens again in a travel lane, I might add. And that was an oversight in the storm drain design system. It was about pressure flow, and I think it was getting relieved when the geyser went up, and then the pressure would build up again, and the geyser, it was the energy grade line was higher than the level of the road. So yeah, you gotta watch out. They were lucky they didn't kill somebody with that grade flowing 50 feet. So here is the rational formula. It says the flow, or the discharge, Q is known as discharge or flow. It's in cubic feet per second. And it's equal to C, which is a runoff coefficient that we can determine, and the rainfall intensity, which sounds so easy and it's a lot harder to figure out, but maybe not so much with MoDOT's method. It's a little easier.
It's a little streamlined, yeah.
Yeah. And then your drainage area. In case of use, just a unit conversion for English, it's 1. Sometimes you'll see this 1/1 or something else for purimetric. So you'll just, actually, what you'd see is the one here. Typically, you'll just see this because we're using English units. You'll just say equals CIA. Has anybody ever seen this before? Okay. So it was originally developed for urban areas and rural areas, wasn't it? Which one is it? I can't remember. Anyway, it got modified and is now used in rural and urban areas. So with the rational formula, we have a few assumptions here. It's only for small watersheds, and typically that is less than 200 acres. So that's probably something, that's the reason why MoDOT uses it for roadway. It assumes that the entire watershed, all up to those 200 acres, are contributing to the flow. So that means the point furthest from your point of interest is contributing flow. The rainfall intensity is the same over the entire drainage area. Now, is that really true if you're looking at rainfall?
No.
No, it's never true. And this is one of the assumptions here, and it's one reason that the method is only used for small drainage areas because of that assumption. And it's important to how we develop our discharges.
You beat me to my question. I was going to say that they assume that because it's the smaller, the 200 acres area.
Yeah, pretty
They've
much.
just decided that, the sensitivity to the differences in the was within a, you know, your,
Well, the realities of what happens in a storm. Now,
Right.
some states will say you can only use this for maybe 150 acres. I've seen it where they only say 80 acres, and some states say 300 acres. So it just kind of depends on your state and your conditions. But
Right.
that is a huge assumption
yeah.
to say that intensity is the same over the entire drainage area. And it's also a huge assumption to say that the storm with a duration equal to the time of concentration produces the greatest peak. We're going to talk about what the time of concentration is in a minute. But if the storm duration, the length of the storm is equal to the time of concentration, that means that the whole watershed is contributing to the flow. And you'll see why in a few minutes. And the frequency of flow equals the frequency of rainfall. And what that means is if you have a 10-year storm, you're going to have a 10-year runoff. If you have a 20-year storm, you're going to have a 20-year runoff. Now, that's not always true. If you had a rainstorm 2 days before, you might have a 25-year runoff with this 20-year storm. But this is the assumption we make here. Okay? Any questions about these? So here are some runoff coefficients, and this is coming out of HDS2, the hydrology, Federal Highway Guidance on Hydrology. And it's also part of this sheet I gave you. That is straight out of HDS2, because you're going to need it for the workshop problems. But let's look at this. So for the runoff coefficient, what we've done is, that they've done with the C, is lumped all of these abstractions together. So we're looking at infiltration, we're looking at soils, we're looking at land use through these categories to come up with the runoff coefficient. So the runoff coefficient can go from 0, where every last drop of water is taken up by the soil or something else, so you have absolutely no runoff, to 1, which means basically you're in a lake. Everything runs off. That's what 1 means. So you're going from those two extremes. And I didn't understand that for a long time. Nobody explained that. They're just saying, here are the numbers. I'm like, what does that mean? So, anyway, if you're in a downtown area, you have a range of coefficients you could use, 0.7 to 0.95. Now, residential areas, single family areas, 0.3 to 0.5. Pavements, 0.7 to 0.95. Well, you might be looking at this and thinking, well, how do I know what number to pick? Well, if you're in a single family area and you have large lots, maybe they're acre lots, so it's not a lot of impervious area, you might say it's 0.3 because a lot of the, and your soils are silts or sands or whatever, most of the water will infiltrate. If you have a lot of impervious area and they're smaller lots, maybe you have townhomes and they're all right next to each other, or single family homes, but you know they have 10 feet between them, then you might go for 0.5. So it's up to you. It's you using your engineering judgment to figure out which one you should use. But it will affect your discharges, like you calculate. Any questions about that? So sometimes, even in a 200-acre area, you might have a little bit of park, and then some single-family areas. You might have streets in there next to your homes, things like that. That's when you have to come up with a composite C. You can't just say single-family homes because it's not taking your streets into account, right? So what you do is find out what the coefficient is for the particular area you're looking at, maybe single-family homes, and you said 0.5, and then you figure out what the area is of that coefficient area that you're using for those single-family homes. And you multiply those two together, and then you look at your streets and find out the area of that, multiply those two together, add them up, and then divide by the total area. Whoa, somebody owes us lunch.
I turned it off.
And remember that area is in acres. That messes a lot of people up. They want to use square miles or something like that. It's always in acres. Okay? Any questions? So frequency, this is for MoDOT, isn't it? This is what MoDOT does.
Yes.
So I'll just go through it quickly. So MoDOT does a correction factor, that C value. Maybe we should talk about it. can you just talk about this one slide?
Yeah, sure. So I think that's just the thought there. I don't know if this is actually recommended anymore in HDS2, but we feel that we still get the same, we get great results from it, so we don't really want to change it. But yeah, so as you know, you have greater storm frequency and greater runoff, you're going to see more water running off those abstractions, those puddles and ponds that might be holding back a little bit of water. As it gets more water flowing to it, that water is going to flow out. It's not going to keep on abstracting as much. Same with your infiltration. It's not going to keep holding as much water in your soil. So we like to correct that C value and bump it up a little bit on the higher frequency storms. So it's just a correction factor. So whatever your composite C comes out to be for the 25-year, you multiply by 1.1, or the 100-year, 1.25.
And if you're below 25, you just use the C factor, no correction.
Exactly, and then also you never go over a C of 1. So you know, if you had like a 0.98 for a road and then you correct it for the 100-year, you can't go higher than a 1 for your C value. So.
Yeah, okay. Any questions about that? Thanks, Colin. And so to get your intensity, you use something called an IDF curve, intensity duration frequency curve. So you can get these from NOAA, but MoDOT has them in their EPG, engineering policy, and they're for different parts of the state. But I wanted to show you what it actually is. So if you know the duration of your storm, or you're guessing at the duration of your storm, actually this is your time concentration. And we're still going to talk about time concentration in a second. So if you have a time concentration of 30 minutes, and this just say is your 10-year IDF curve. You go up to the curve and come across and you find an intensity of 3 inches. Now that sounds real easy, but there are formulas here. Well, it's different. So yeah, that's the idea. If you went to NOAA, Atlas 14, or NOAA in general, you could pick a spot on that wherever you want your site to be. And they will make all of these curves for the 2, 5, 10, 25, 50, 100-year storms, even 2 and 500-year storms. And you can download that. But like I say, MoDOT has their own IDF curves that they develop. So use those. And here is an example of it. And they find the intensity a little bit differently than how we teach the rational method. And here is how they find it. Intensity is equal to A, one of these constants, divided by B, plus the time, that TR is time of concentration, and the M they give you. So if you have a 10-year storm, you go in, you find your A is 25.5, your B is 2.06, your M is 0.61, and you have to find the time of concentration. And that will give you your intensity. And like I remember, this is for the central district. I'm not sure what that means.
So yeah, we have multiple districts, and we have an IDF curve for every district. I think our hydrologists actually looked at doing them in every county, and then kind of compiled them into general ones for each district to be used.
Okay. How many districts are there? Seven. Okay.
Northwest, Northeast, St. Louis, Kansas City, Central, Southwest, Southeast.
You get the gold stuff. That's good. Okay, so yeah, you go into your EPG and find your district where your site is. And use that idea for. So again, you know how to come in here and find it, right? Once you find the time of concentration, you're going to be the 10-year, which is pretty cool, right? I guess you could come across and do it like this, right?
Yeah.
Or you could use that formula.
Exactly.
Yeah, so you come in at 30, go up to your 10-year, come across and estimate of your intensity. So when we talk about time of concentration on the national taking of it, it's the time of travel from the most hydrologically remote point in the watershed to the outlet. So think of a drop of water going from the most hydrologically remote point in the watershed to your point of reference. And when I say most hydrologically remote, I'm not saying the thing that's the furthest distance. I'm saying how long does it take that drop of water to get to your point of interest. If you're on a mile, well, you have a 200-acre watershed and it's a flat slope here and a steep slope here. Even if this is closer in distance than the steep slope area, edge of your area, This might take longer because it's on a mild slope and the velocity of the water is much slower. Okay, so think about that when you're thinking about time of concentration and where that time of travel is from the most hydrologically remote point to your point of interest. So in HGS2, our hydrology manual for federal highway, we break it up into 3 components, the rational method. We have overland flow, or what we call sheet flow. And you ever seen sheet flow? Do you know what I'm talking about? A lot of times you'll see it in parking lots. If it's on a little bit of a slope when it first starts to rain, you'll see the water just sheeting down and then it starts to come together, right? Well, you'll see that in the natural landscape too, the sheet flow. Not in every landscape, but in some of them. The water just kind of moves as a sheet until it starts going into shallow concentrated flow, where it finds rills or gullies and starts to gather together. And then we have channel and pipe flow. So there are 3 different components. Now you could have all of these components. You could have 1 or more of each component, not so much overlap, but 1 or more of these 2, or you might have just pipe flow, you might just have this one. You know, it just depends. You have to look at your drainage area and figure that out. So with MoDOT, they don't have sheet flow. You don't consider sheet flow as part of the overland flow.
Overland's essentially sheet flow, the way we look at it.
Oh, so you don't have shallow concentration.
Essentially, yeah.
So they
Kind of
call
like
it sheet flow overland or ditch, and then it goes into ditch and open channel flow, and then you might go into storm sewers. So again, you might have 1 or more of these, you might not have them all. Okay. So let's just look at this drainage area. So here's our outlet, and we have a little tributary here, and we have another tributary here with another one, a flow. They're showing a flow path. This flow path for B looks like it's going through a natural area, or fairly natural. This one is going through, I don't know, it looks like an urban area, more urbanized section, and we have a storm drain here. Here's another storm drain. Here's your main stem, and here's a tributary. So if you wanted to find the flow path of this one, would you say, I don't know, you might say, I think it's C. But could it be B? I don't know. You'd have to look at it and see what are the circumstances here. Do you have a lot of vegetation in your area where you might have that overland flow? Is it going to slow down? Maybe you have grasses here on the steep slope and it'll go straight over to your tributary. So that's what we're talking about. This one, if you're in a storm drain, do you think it's going to move faster or slower? Faster. Yeah. So that's what we're talking about. So this might be overland flow here, and it goes into your channel and it comes on down. This one, it really just starts in your storm drain and it's going to your channel. So, you know, you have to look at all those segments, those components, and figure out what your ton of concentration is. I don't guess any of you use WMS, do you? Watershed Modeling System. Yeah, it might be hard to do for, you can do it. It's a software program that Federal Highway has that actually you put in the DEMs, the digital elevation map, and you put in where your site is, and it outlines your drainage area. It tells you how big it is, and if you want it to, you can put little markers in your drainage area, and it'll show you the flow paths, and you can figure out which one is the most hydrologically remote one. If you have a whole lot, like 200-300 pipes that you're looking at, it can get a little confusing, but they've improved it somewhat. You might look into WMS. And it's free as long as you're a MoDOT employee, a DOT employee. Federal Highway subsidizes your licenses, so you can download it from the Aquavale website, and when then you register, you say you're a DOT employee, and they give you a license for a year. And then you can review that. Might look into it. So this is showing sheet flow, just to give you a better idea of what it is. So we have rainfall coming down on some surface. We have a bit of a slope. Here's your flow length, and everything is just coming off in a sheet. That's basically what it's showing.
What was WMS stand for?
watershed modeling system. And if you want to look into getting that program, the name of the company, you just go here and then go to software and pick WMS. Well, you might talk to, I don't know if you can actually download and install it on your machines. I would not be able to do that. I'd have to get IT to help me. But you might talk to your supervisors if you think it looks good to you. And there are training on it, but they have a lot of tutorials online. They have a wiki page to answer questions, all that kind of good stuff. And it makes outlining your drainage area so much easier. Okay. So this is shallow concentrated flow. I don't think you guys have this in your workbook. My apologies. But all this is showing is that it's going from sheet flow, and then it's all the flow is concentrating into one area, into your rill or gully or whatever it is. And then it comes out that gully. And to figure out channel and pipe flow, in your channel, you would use the Manning's formula. Has anybody heard of Manning's? Well, a few of you have. This, Robert Manning was a self-educated engineer in Ireland in the late 1800s. And he became the chief engineer in some little Irish town or city. And he came up with Manning's formula. And I'm not showing this quite right. Eric, don't we need 1 over case of U in that velocity equals?
1.49 over n.
Yeah.
Over the n. I don't know how that happened. I took it straight from the NHI course. So that velocity equals 1.49 over your roughness times r to the 2/3 s to the 1/2. That's how you find the velocity in a trapezoidal channel or in a pipe. And when you're looking at hydraulic radius, which is this R, the R is equal to the area divided by the wetted perimeter. So your wetted perimeter in a pipe is how high your water is, and it's that perimeter. Okay? And the same thing in a channel. Your wetted perimeter is however high your water is. You start your perimeter measurements there, go down, across, and back up. Okay? And Calvin's going to take it from here. He's going to talk about the Missouri method.
All right. Thank you. I was going to talk about time of concentration a little bit because we changed the way we do it last year in the EPG. I figured before jumping into how we do it in our EPG guidance, we just run through how they do it in NHI and the HDS2 there. Because that's how we're taught that way in NHI, and we're also kind of taught that way in school, so that's kind of conventionally how we think about it, so it'd be a good starting point. So does everybody know, does anybody have the HDS2 on their computer, or know where it's at? We have it out there online. Whenever you go on SharePoint, if you click in the top right under Bridge Division, BR, and click Hydraulics, it'll take you to the Hydro Web, and then there's all kinds of PDF references out there, and floodplain permits, pretty much anything you can think of hydraulics, but there's a PDF version of that out there for you. So you'll go find that, and the velocity method's there in section 2.6.2. We'll just run through how to do that really quick. We're not going to get too into it though. So you have the 3 flow regimes, as we previously mentioned. You're going to have your sheet flow, your shallow concentrated flow, and your channel flow, or pipe flow. So with the sheet flow, HDS2 gives you this equation. Okay, so you have alpha is a unit conversion there. Then that's going to be your overland flow roughness coefficient. It's a little bit different than Manning's roughness. You want to think about it because you have this laminar sheet of water real thin. So you're going to have a different roughness coefficient than Manning's would be because that sheet of water going through grass or tall grass, it's almost like it's impeded like going around the forest because the water's so shallow. So you want to take that into consideration. Make sure you use the right values there. Everything else is pretty similar and basic. We have length, slope, then here's this I. intensity, which is what we're looking for with the rational method is, we want CIA. And that's what we're trying to find with time of concentration. So that's kind of confusing there. You have to pick a reasonable time of concentration, plug it in for I, and then see how close you get. And then it's kind of like a guess and check iterative method. So we don't necessarily like that a whole lot when you're trying to just plug and chug and get a right answer. So there's some spreadsheets that'll do it for you. And then also they came up with a little bit better method in HDS2, or more streamlined. I think this was the TR55 method. And here instead of I, they changed the exponents a little bit too, but everything else stayed the same. They use P. And this P here is a 2-year, 24-hour rainfall depth. And you can go to NOAA Atlas 14 and find rainfall data for your specific site there. And that's going to give you your 2-year, 24-hour rainfall depth. And then from there, you're just plug and chug. You get your answer, no iterating or anything. And moving on, you do shallow concentrated calculation, which for that, you're going to calculate the velocity similar to how we did the channel flow, only you're not really taking into consideration the geometrics of the channel as much as just the roughness of whatever it may be, grass, parking lot, the vegetative cover. You're going to take that, you're going to look up a shallow concentrated coefficient, and that's there in the HDS, the tables of coefficients. And then from that, you're going to get your V. And so that velocity, you know how long you're going to be in this shallow concentrated flow regime. So the time is just going to be the length of that divided by the velocity, and then converted to minutes. That'll get your shallow concentrated flow. There's actually the equation for that. It's time equals length divided by velocity times 60. And then your channel flow is going to be the same deal. You'll go use Manning's equation for your channel or your pipe for the actual specific geometry of what you're looking at. Length divided by that converts, that gets you your minutes. And then your time of concentration is going to be the sum of those 3 flow regimes, your sheet flow, your shallow concentrated, and your channel flow. And that's how it's taught by MoDOT. You see it in the HDS2. Our APG is a little bit different. It splits it up between rural and urban. There's 2 different ways we look at it. On the rural side, we do Kirby Kirkich, which that's fairly new. We used to just do Kirkich for all of the rural time of concentration, but now we're actually bringing in a different method to look at it. And on the urban side, we do Kirby Hathaway, and we add in the appropriate channel or storm and sewer travel time. So I know that's kind of Greek right now. We're going to get into these methods and see what they actually are here. So like I said, it changed in early 2018. Rural water time, the time of concentration was just done by the Kirkich method. We had a NHI class a couple years ago. Some gentleman teaching that was looking at our guidance and said, Kirkich is a great method in the right situations, but it's probably not the best method to use for the whole state. It might give you might give you shorter time of concentrations than you're actually seeing. And so we were working on a drainage study at one point and looked into it. We ran time of concentration just using the Kirkich method. And we also ran it again with using what's recommended in HDS2, the 3 flow regimes. And notice there's a pretty big discrepancy between the 2. So we looked into how Kirkich was calculated. It comes from a small rural watershed in Tennessee. One farm developed the equations for the Kirkich method. And this gentleman, he broke his farm out into, I think, 12 different sub-catchment areas. And he actually measured his time of concentration from these. They varied from about 4 acres to 120 acres. And they were real steep slopes with really good defined channels. So if you have steep slopes with good defined channels, it's pretty accurate. And we start looking back to see, how long ago we recommended using the Kirkich method in these rural watersheds for time of concentration. And the same wording was verbatim all the way back to the old PDM, which was before my time. I think it predated the EPG. So who knows how long? I mean, we could have been using the Kirkich method since he came out with it in the 40s for a while. So we kind of looked at updating that a little bit. We started looking at what other states have done and just trying to find what might be a better, more accurate method, because Kirkich is nice that it's streamlined and it's really quick and easy to use. So we wanted to keep something that's relatively simple and easy if we could at least get good numbers with it. So we looked and combining Kirkich for this channel flow time that it approximates pretty well. We found that for Missouri's topography, if we include Kirby Hathaway for the overland flow, which that's essentially accounting for that sheet flow at the top of a watershed, before it actually kind of finds its slope and down its divide into a channel. We were actually getting really close numbers to what we do when we break it into the 3 flow regimes. And it's a lot simpler, a lot more streamlined. So we went forward and actually changed the EPG guidance for that. So I'll jump into here and show you guys the equations and how to use them. So Kirby Hathaway, this was already in the EPG, it was just on the urban side of this. So now it's that we're combining this, it'll be both on the urban and the rural as well. Unless if you're in a place where you do have really steep valley sections, you might not use this. It's still up to your judgment. You could use all coefficient if you felt it warranted it. But so it's really a streamlined equation here. You can see that there's no iterating. You do have to have your roughness coefficient. That's going to be your overland flow roughness coefficient, just like the sheet flow was. You have your overland flow slope. These are very short distances too that it actually does overland flow. It's going to start to kind of get into swales or kind of gullies over a short distance. I think our guidance says, it's less than 300 foot and usually much shorter than that. So a lot of times I'm looking at maybe 50 to 80 foot to start off when I'm looking at overland flow. It's really specific to the site, but it's a relatively short distance. So you know your length, you find your roughness coefficient, your slope, and that's going to give you your overland flow time and concentration. Which I actually had in there. I recommend means less than 200 foot. They said usually much less than 500. I've never seen one that's 500. That'd give you a pretty high time of concentration. So yeah, like I said, maybe start at looking 50 to 80, but whenever you actually see that topography, say you're at the top of the hill, whenever it starts to fall off and you think you're actually going to find some gullies or some of that water is going to concentrate. Here's the roughness coefficients for overland flow. We'll have an EPG there. And then for the curvage method, this is what was originally in there. We still like to use just using it in combination with that Kirby Hathaway method. You'll notice here there's no roughness coefficient. It's not even taken into account. It's just based on 2 factors. It's simply the length and the slope of the watershed. And so that's, I think, why they recommended we look at it a little closer and think about it a little further. Maybe it's not great to use across the board everywhere in the state because it just doesn't take enough into account. But from what we found, it does work really well. It just pretty much, it kind of lumps that shallow concentrated and that channel flow into one time of concentration essentially, which is a little different. But if you're questioning it, I'd definitely run through both and see how close you get because from my experience, they come out pretty similar. And then so your total time of concentration, that's just going to be the sum of those two. And then also, whenever we updated that part of the EPG, we added a low slope correction factor. So anytime you have flat slopes, and these are really, really flat slopes, to where the water is going to have trouble rolling off. So if they're flatter than 0.2%, you can adjust them by adding that 10,000ths of a foot per foot. So it's a pretty small adjustment too, but it's going to help you some in those really flat areas. And say anything between 0.2 and 0.3%. Engineering judgment should be used, but if you're that flat, you should probably throw that adjustment factor in there too. A lot of us won't even see slopes this flat, but maybe in Southeast District or out there. Yeah, I heard the drainage method there just to try to make the ditch so long to wear the water out. So here's just kind of an example of that flat slope correction factor. So we have our watershed divide here. We have our outlet over there. There's about 1,050 feet between the two. This is a pretty rudimentary example here. But we'll say that the top of this hill here, for 50 foot, we're going to be having a slope of 0.2%. This isn't to scale. And then for 1,000 foot, we're going to have a slope of 1.5%. And so looking at correcting those, that first slope is so flat, I think we will give it the correction factor. We'll give it a little bump there. Next slope, we'll just leave it how it is, because water's not having any trouble running off of that. I'm going to run through just a quick time of concentration example. Look at Kirby Hathaway here for that first 50 foot. I just went ahead and assumed that N2, I said we're looking at pasture there just so we could actually run a number on this. And then curvage there. We know our slope, we know our length. We don't have to assume it in with curvage. And so plug those numbers in that we have. When we get to that first 50 foot running through pasture with that laminar flow, we're looking at about a little over 12 minutes. And then for the curvage method, now that we're kind of in those swales, we're actually running down at 1.5% slope. We have about 8 minutes of that travel time, which, that seems kind of 8 minutes to travel 1,000 foot versus, what was that previous one? 12 minutes to travel 50 foot. You have to take into consideration too how flat it is, and also that you're running through pasture at the top of that hill. All things in consideration. So our total time concentration would be those two numbers sum together, 20 minutes. You take this, you go to the IDF curve in whatever district you're in, find out exactly what the intensity of that storm is, and then you can find your peak runoff through a CIA. The area of the watershed, the composite runoff coefficient, and your rainfall intensity. And then on the urban side, it's essentially the same, it just doesn't have the curvage method involved. It's just this curvy Hathaway. And I think the assumption here is that you're going to be an overland flow until on the urban side you're going to find a storm sewer or a ditch. You're going to convey water somehow more than just running across a field for long amounts of time. But there might still be a case on the urban side where you have to use your judgment to maybe look at using the curvage method or how we normally do it on the rural side if you do have a long, maybe through a park or something like that until it finds a drainage ditch. Still engineering judgment there. Kind of whatever you feel is appropriate. But this is what our EPG is doing, this curvy Hathaway combined with channel or storm sewer, which on the channel you'd just be using this or storm sewer as well. You use Manning's to find your velocity, and then the time is going to be the length of that flow regime divided by that velocity. And then we also have the runoff calculations in the R drive. Does anybody use that for flows to calculate their flows? It's an in-house program we have. It's pretty handy for rational making because it has all those IDF curves stored in it. And the way it works is you can put in all your sub-areas. You can put in the acreage and the runoff coefficient, and it'll go ahead and make a composite C for you, so you don't have to do that by hand. And then it also finds all your intensities for the different storms from the IDF curve based on the time of concentration you put in. And you can also use, it has calculators in it to calculate the time of concentration. So as long as you maybe suggest comparing what you calculate with what it calculates, so make sure it's all right. But it just kind of, it's going to save some time on calculating deep runoff flow, so you don't have to go to that IDF curve every time. Just kind of streamlines the whole process. And we'll show you that calculator here after the lesson. We'll do a workshop problem and try to get the same numbers with the calculator as what we did in the workshop. Let me example this. Back to you, or?
You can go back to me, that's fine.
Okay.
Great. I think that's the end of your part though, right?
So, yeah.
Thank you. Good job. I think you did a much better job than I ever could. So we're going to look at an example using the rational method for the surrogate method. We're going to look at an inlet. And the drainage area, the area is drainage void, and they give you the time of concentration, which is 25 minutes. And we have a 2-year IDF curve that we showed previously from the central district, and this is how you find the intensity. And we're being asked to compute the design flow for a 2-year event. So we have to do composite C here because we have single-family residential and we have streets. So they give you the area of each of these sub-areas, and they are giving you the C value, and we're going to find the composite C value. So how we do that, we just add up the areas. We have 3.4 acres. That C, to get the composite value, you do the C value for that area times its acreage, plus the C value of the other area plus this acreage, and then divided by the total acreage, or total area. So you can see it's there is 0.4 times 2, 2.4 and 0.9 times 1. And that comes up, we come up with a C value, a composite C value of 0.55. And then to get the intensity, we're just chugging and plugging, and we got these variables from the IDF curve that we showed you earlier. And so we already know what our time of concentration is, and I want to point out that TR is a very odd way to say time of concentration. It's usually T sub C. That's how you normally see it. Do you know why they put R there?
I think they mean time of runoff maybe, but it's confusing.
Yeah,
and
it's a little bit
inconsistent, so.
confusing. I was looking at my calendar, what's this? So anyway, we plug in chug and we get 2.42 liters per hour for our intensity. And so our Q then is CIA. So our C is 0.55, our I, we just figured out, we was wrong, that should be 2.42. Times 3.4. So if you put the correct number in there, what do you get? Anybody?
4.5, right?
4.5. So I might change that. Another little mistake. Thanks. Okay, so any questions about how to get a composite C? Because you're going to be doing this in the workshop, so I hope you understand. So this is going to be our workshop problem. And, well, let's back up. Do you have any questions about what Calvin talked about or about the ration method in general?
Just to clarify about the channel flow, so in the that method, which is the Klappers method, so it's incorporated like the shallow flow and the channel flow,
Exactly.
both in the same equation,
Yeah.
without considering that coefficient.
Exactly.
For the channel flow, right? Whatever
Yeah.
the channel looks like.
So Cal, can you repeat that so everybody hears?
That's essentially what it does is, so it's taking it from that overland flow all the way to your outlet there. So whatever happens in between there, whether it be shallow concentrated or going through a culvert or a channel, all that is essentially lumped into your time of concentration. So yeah, it incorporates both those methods. But a lot of times on the rural side, you'll be looking at a pipe or a culvert. So it's not really like storm sewer or culverts that are really going to get incorporated into that. You're going to be looking at normally a pipe in a ditch or a culvert in a ditch or a crossroad pipe, you know. So it's not, so I might incorporate some of that ditch that's going actually to that culvert. It's gonna, yeah, not take into account the actual geometry of that ditch as it would with Manning's equation. You break it into the flow regimes, but
So that like, is there certain assumptions that when we can use it, like is there comparable to Manning equation, like if our ditch, I mean, it depends, right? Like there's different ditch configuration might be there, so how can we, like is there assumptions on that this method that we should like follow?
you know, in our EPG, it really just says that that's the accepted method to use in that situation. But you know, if maybe you have a case where you're looking at it and you think that maybe there is going to be a big difference between the different flow regimes, and maybe you're spending a lot of time in a really defined channelized ditch before you get to that crossroad pipe that you're analyzing, then maybe you do look at using an HDS tool and breaking it into the three regimes. But you know, if you ever do go that route and actually run all three flow regimes and calculate it, I'd recommend running through our guidance as well and just comparing it to that to see how close you get. Because I had to do it one time just to kind of convince myself that it was actually pretty accurate and pretty close to what we come up with. But
And we can compare them to, like, we can use that for
Certainly. Yeah, exactly. And so we can use what's recommended in HDS too. It's just our EPG doesn't go into detail with it. So I think they don't want to get confused between the two methods. So they really just kind of say where to find it, that it's an acceptable method to use. But you're always more than welcome to try that. And if you think that maybe, yeah, there is, it looks like, you know, you're kind of coming down this hill, you're going to have goalies, and then again, this well-defined ditch for a quarter mile until your culvert. Exactly, and then I'd probably maybe look at using that. And so, yeah, if you have different slopes too, you know, and they break really drastically, maybe it lends itself more to that method.
So something else that I was thinking about with this IDF curve, and it looks like you're asked there too. So when you get a time of concentration, you always want it to be, according to MoDOT, at least 5 minutes. And the reason is because your time of concentration influences your intensity. And you can see at the start of the storm, when it's only about 5 minutes, you can see that you got this, the intensity is really high, and then it drops off as the storm keeps going. So you don't want to go below 5 minutes because it's an unrealistic intensity that you would get, okay? So that's why almost every state says at least 5 minutes is your minimum time. If you're coming up with a time of concentration less than that, then you go to 5 minutes. Right?
Correct.
Some states will say 10 minutes. It just depends on the state. Typically, it's 5. That's what we say. So I'm sure you're aware of that. And that's why all these curves are starting at the 5-minute mark. Okay. So does everybody understand what that conversation was? Any questions about it? Okay. So we're going to look at this example, and there are a few things I want to talk about. There we go. So this is the example. We have already given you inlet A. We just did it, where we found 4.5 is the flow going to this inlet. Now, we have inlets on the surface of the ground, and below that we have pipes. So you have to remember that when you see time of concentration equals 25 minutes, that is the time of concentration to the inlet, not to the pipe. It's the time of concentration to the inlet. Same thing here with 10 minutes. That is the time of concentration to the inlet. So when we ask you for the time of concentration in the pipe, B to C, it's not going to be, it might not necessarily be 10 minutes. The other thing you have to remember is that if you are trying to find the time of concentration to pipe, CO, what you have to do is you don't look at just the time of concentration of the area going to inlet C. You have to look at the entire area that's contributing to the flow in the pipe that's going from C to 0. So if we, and you pick the longest time of concentration as well. So if I'm saying what's the time of concentration to the top of pipe CO, what would you say is the time of concentration?
26 minutes,
Right.
because it's 25 minutes for the time of concentration to point A, plus 0 to cross the street to pipe B, and plus 1 from B to C is 1 minute.
That's the travel time in the pipe. It's 1 minute. And if you don't do that, you don't want to add up flows from B, flows from A, and flows to C. You don't want to add those up, because if you do, you're being too conservative and your pipes are going to get really big. So, and that is because your time of concentration is 25 minutes and it's negligible through here. So it's going to take about 25 minutes for the peak from region A to get to this area underneath the inlet to go into pipe BC. Now the peak for this area is coming at 10 minutes. So this peak, remember the hydrographs? This peak is already passed by the time this peak gets here, which is why you don't want to have them together. And it's the same thing here. This peak, this is 20 minutes. That's when the peak from this area comes through. But this peak is already passed and this peak hasn't happened yet. So never add up the discharges from different areas. You always want to look for the largest time of concentration, because that means 25 minutes, this entire area is contributing, and you're already taking into account the flows you would see from these other areas. Okay? That's really important thing to remember. A lot of people want to just add up discharges, and it's not the way it should go. It's way too conservative. It costs you a lot of money because your pipes have to be so big. So we're going to turn you loose here, and while we'll go over, just talk about the lesson you've got. You can turn the page. There's exercise lesson 2. And so we are showing you this graphic here, basically, and I think it says 4.9. You know, I think for, let me just see here. I might have to just use 4.9 for that. No, don't worry about it. Okay. So if you turn the page, go to the second page, you are looking for the 2-year flow, and I want you to give me, you're gonna have to figure out what the discharge is at inlet B, and then inlet C, and then you're gonna find out what the discharge is at pipe BC, and then pipe CO. And you can see that we gave you a table, and it says basin inlet land use area C. The last 3 for C, you're gonna have to find those Cs, and that's the paper, that handout I gave you can look in there. And we're suggesting that don't obsess about it, and so everybody gets the same C value, just take an average of that range and use that C value, okay? So if you fill those 3 in, and then you can start figuring out what the discharge is at inlet B and C.
What is asking, don't we need an additional time between CO?
Between CO, why would you need that?
What is the time it can take?
We're just asking, what's the time of concentration at the head of CO? We don't care what the travel time is, because we're trying to figure out flows. So the only flow coming in is at this inlet. There's no flow coming in here. We don't need a time to travel. Okay? So I'll come around and help you if you have questions. Yep.
What's the 0.5 next to QA? 0.1 next to QA.
That must be the, let's see. QA equals, I don't know, I think that was a mistake. Just get rid of that. Get another mistake. And to find the intensity, we gave you the equation, so you can find the intensity for that 2-year storm when we're using the central district area equation. We gave you the areas, didn't we?
A, B, and G are right.
Yeah, I'm sorry, it's in mine, it's not in yours.